evening, everyone. I have the burden to be the last speaker of today's session, but I am sure I can add some color to this maybe a bit dry topic. And I would like to talk to you about creating your own chemical space, like making the first steps. And yeah, what steps are necessarily needed to create it then in the end. Okay, let's go quickly through the agenda. So first of all, I will talk about our powerhouse for creating chemical spaces, which is CoLibri. And then I will talk a bit about how to code your own reactions, give some tips and tricks and how this all reaction and coding works. And finally, I will give you some additional information and also where to get help when you are like a total beginner. So let's start with the first section. Yes, so we've heard before now in all of the talks that the ingredients for chemical space are building blocks and reactions. And by using CoLibri, which is a purely command line package software suite, it contains all these little 4 tools that I will briefly explain. These are necessary to build and in the end your chemical space, which is this .space file that we also have been talking about. So the ingredients for your chemical space are simple. It's the building blocks and the reactions. The building blocks can come actually from any source, but to make your space also tangible and accessible, you would rather choose a vendor that has like in-stock building blocks. So commercial libraries are actually perfect for that. You should also pay attention to delivery times to make it also like make on demand. Yes, and regarding the reactions, they should ideally be robust, one-pot synthesis that does not require an intermediate purification step. And then this all in all would lead to reasonable compound prices in the end, because we've heard also in the talks before, we want to save money in the end. But you probably know your chemistry best. Okay. So let's dive a bit into the components of CoLibri. You need to provide for this command line application your input, which are your coded reactions and your building blocks. And then the first step would be to use the reaction synthesizer that generates a fragment subspace for each reaction from these SMERCs or RXN, so the reactions definitions that we will talk a bit about in the end, and the respective building blocks that you want to use as EDOTs. Then you would use the frag space merger, which uses the output from the reaction synthesizer and combines all of these little multiple subspaces into a single consolidated space. That is what we typically call, depending on the file types that we have, a classical fragment space that you might have heard of, used of in before. The third part is the Spacelight DB creator, which generates a topological space. It has a special file format, and that is actually needed to support these molecular fingerprint searches. And that's why this part or this tool is needed to create the topological part of your chemical space. So having made all this, in the end, you have the frag space converter, which converts all the fragment spaces, so all these single little spaces in this consolidated classical space, together with the topological space file format in the end into your final chemical space. So all of this in the end leads to your .space file, which is a single file that can be then used either for chemical space docking or for the searches. Okay, so once your space is ready, we've heard it today, we have this trinity of our search algorithms, And we heard also now by my colleague Philo that this file type is then can be used in multiple ways within our BioSolveIT environment. Okay, so this may be a bit messy. So now let's focus on how to code your own reaction. So how to actually get there. So the reactions are usually written in SMERCs or RxN using smarts. To give a brief distinction on that, SMERCs or RxN basically means it's based on the smarts code, and it describes how parts of the molecule change. So it describes a reaction or a transformation, while in contrast to that, the smarts describes the substructure or pattern itself. And to add another term to all of this, we also all of you might know SMILES, which describes a molecule. A SMILES is always unique for a certain kind of molecule. So now that we have distinguished all of this, we have some little helper tools to guide you how reactions can be written. For instance, we mostly, like internally, we use the smarts editor, which helps you to visualize and test your definitions, so your substructure patterns, and test them if they are correct, or if you want to add additional atom environments, which we will also briefly talk about. But these only work for single molecules only, so not an entire SMERCs code. In order to test this kind of SMERCs code, you can go then to the Smart Plus server, for instance, to visualize and understand the complete reaction encoding. It gives you also errors and says where a reaction definition is not correct, some kind of a syntax error. If you want to have it even more visual, you can also use Marvin Sketch that also shows you the entire environment definitions visually. You can export out of Marvin Sketch these SMERCs or RxN formats. That's the another file format for reaction definitions, but it requires a license since 2022. So these two on the left are free. This on the right isn't. Okay. So the basic skeleton of a reaction definition is listing the reagents on the left side. So here we have reagent 1, reagent 2 separated with a dot. And then we have these two arrows that in the end lead where on the right side the product should be. So this is the basic skeleton. Okay. Then you will add your molecules that you want to, for which you want the atoms to react. And SMERCs functions basically like a cooking recipe. You tell the system what you want to keep and what you want to replace. That's why we also see all these little numbers here. I mean, obviously, you see this is the basic amide coupling. And we have labeled the atoms that are going to react and then be combined finally in the product. Then we add a little code to it. And at that point, I probably already lost half of the audience, but I will explain one example in brief. What we see here are the mapping labels, which match the atom definitions that you see here in the 2D picture. And they have to match so that in the end, when you see here on the product side, you have all of the numbers next to each other in the correct order. So your product is correctly assembled. And we see here on the bottom, this is a complete reaction definition, so a complete SMERCs code. We have the reagent 1 here in dark blue. Then we have all the definitions that we want to have for the second reagent in green. And then in light blue, we have the product. So if you can use any text editor to code this. Obviously, this is just a bunch of numbers and letters and signs. And then you can visualize it in the smarts editor, paste it there, and use it for debugging. Okay. So let's give a little more detail to it, starting here with the nitrogen that is part of this amide coupling. You see here a screenshot from the Smarts Plus server, which also tells you which reactions definitions have been added. Because if you ask a chemist on an amide coupling and you ask them, okay, what kind of properties should that nitrogen have? Then the chemist would say, okay, I want a primary or secondary amine. Yeah, but the nitrogen must not be part of an amide, an amidine, or a thioamide. And then you, as a computational chemist, or as the person who has to code the reaction, would say, okay, yeah, how am I going to code it in a way that I can explain it efficiently to CoLibri so that it understands what it should combine in the end. So this is why we see here the code on the left side. This is what you end up with in the end. But let me explain that in more detail. So you would ideally start with an amine, meaning I have here the nitrogen, and then you have the $sign, which says, okay, in this environment of this nitrogen should be a carbon. So it can be aromatic or aliphatic. That's why it has this #6. And then it has this mapping label that we already know. But then we would go and check within our building block set, okay, is this reaction definition sufficient? What building blocks will actually match? And we see that not only do we have the primary or secondary amine that we want to have, but we also have a hydrazine, an amidine, an urea, or a tertiary amine, so things that we don't want to have. So obviously this definition here, that is not enough. So we should further specify that nitrogen should either have 1 or 2 heavy atom neighbors. So we add to our reaction definition D1, so D stands for heavy atom neighbor, D1, which says in the environment of this one connection, heavy atom connection that I can make, that should be this carbon that we had previously. And then in the second heavy atom definition, then we say, okay, then it can be 2 carbons. Okay, we check again, is this definition sufficient? What building blocks will match? And we see here that we already ruled out this tertiary amine, but we still have the urea or the hydrazine in our definition, so that's not enough. Okay, so we have to add more information for the algorithm to in the end properly function. Okay, so we further specify that exact same nitrogen should not be an environment of a carbon with a double bond to another nitrogen, a sulfur, or an oxygen. So we further extend our code again, and you see that this term here was added, so it's an exclamation mark that says, and not $sign, which says the environment of that nitrogen bound to a carbon should not have this double bond either to an oxygen, nitrogen, or sulfur. So far, so good. We check again, is this reaction definition sufficient? And we see that we rule out all of these unwanted substructures and just are left with the primary or secondary amine. So far, so good. This is the reaction definition of one atom that is going to react in your coding. Okay. So this is now all like based on simple text. But if I want to check and see what actually matches and does not match, we have a very nice feature actually in the Smarts editor where you can type in your definition here, and then you can add a set of building blocks and set your definition as a filter, and everything that is green, you see how the building blocks that match. And if you set the filter to red, then you see all the building blocks that didn't match the definition. And this is actually very, very helpful to see, is my reaction or my atom definition, is that precise enough? And once you have done that with your reactants, then you would write the entire SMERX code and then go to the SMART Plus and further debug. So that is actually the most time-consuming and first part of your workflow when you want to create a chemical space. Thereafter, you would proceed with the reaction synthesizer to generate for these fragment spaces. You can also, within the command line application, optionally enumerate some products. CoLibri has a separate flag for that. And then you can see the products and see, do they match what you have envisioned? Is my reaction definition sufficient? And then you would further continue with merging these multiple fragment-based spaces, create a topological space. In the end, you can also do some debugging with the reaction synthesizer. You can ask for a large or a detailed output of the log files by setting the verbosity up. And in the end, you finalize and pack your space using the frag space converter. Okay. Let's also talk a bit about the beauty of the combinatorics. So you might ask yourself, okay, I have coded one reaction and now you can add and combine the building blocks that match the definition, obviously, but you can easily scale it up. So imagine you have 5 times 5 building blocks. If we stick here with the example of the amide coupling, that already gives you 25 combinations. So if you keep adding more and more building blocks, the larger the numbers will get. So 1,000 by 1,000 already leads to 1,000,000 compounds. So that's really where these chemical spaces have this explosion, or how they actually get so big. But this is only for one reaction. So this scalability point is actually a huge benefit that you have when you are looking at enumerated libraries, because what we see on the left is just also one reaction type, as I said, the amide coupling. But we have different reaction types. We can do different types of couplings. We can do ring closures. We can do multi-component reactions where you have 3 to 4 building blocks, meaning when you envision the reaction definition, you have like 4 positions that lead to your product. And then you can also go and mix and match all these building blocks that you envisioned to be for the first position, for the second position, and for the third position, and so on. So it can be entirely complex. And then on top of that, you add the layer of adding more and more building blocks that match all of these definitions or are specified for certain kinds of definitions. And also by adding more and more reactions, this combinatorics explosion is actually taking place, and that leads to these large numbers of possible compounds. And with all that we have learned about the chemical spaces, how large they are, and then these compounds are even purchasable. So that is where, yeah, it makes all our lives easier in the end. Okay. One important point also to consider is how to generate novel IP. I mean, by default, chemical spaces already generate novel IP. As Alex said, we don't know what's inside the spaces. These are probably combinations that you have never seen before. But you can also, if you are creating your own chemical space, you may mix building blocks from different vendors, plus your own proprietary building blocks to increase this high level of IP. So you can use enamine building blocks, your own, then you can use building blocks from a different vendor and put them also in your space. And that is where you really create a space that is of high value to you. What also contributes to that is are unique reactions from your in-house chemistry. So things, very specific reactions that your chemists know how to do. And these help to generate a very useful hunting ground for you to find novel molecules. And we also, the group of the ZPH, which is also kind of collaborating with us, also published in 2022 a study where they showed that actually all of these chemical spaces that are out there have very, very little overlap. So they are very unique in their kind of how they are built of, what reactions are inside there, and what building blocks are inside there. And also this study here by a group of from AstraZeneca also showed that larger spaces are actually better. So they showed here that the number of hits and the novelty of hits the novelty of different scaffold actually improves when the spaces get bigger and bigger. So yes, this is why also Alex said in his talk, chemical spaces in the end are better. Okay, coming to the last part of my talk, tips and tricks and where to get help if you want to do your own chemical space and you start with basically no experience, is you can find SMERCS encodings here on this daylight page. They also give you a lot of information on the theory, how SMARTS works, what all of these symbol means. I mean, I glossed a bit over it now, but if you want to really deep dive into it. And we also have this cookbook that was also mentioned along in the Drug Space Symposium that we created, where you have all these reaction definitions, also visual representations, also with a paper attached, so a reference, and then directly the code there. So that is where you can get started. And also within the CoLibri tool, the reaction synthesizer comes along with a small text file, which has predefined functional groups that you just can use and copy and paste for your own definitions. And to give you a bit of a glimpse what's inside the cookbook, you see here all these type of reactions, so couplings, substitutions, ring closings, core reactions. So there is a plethora where you can choose reactions from that you want to incorporate, but also to get some inspiration, of course. Okay. Finally, some lessons learned, I would say, especially from us. You should rather think in substructures. So identify a minimum substructure that precisely defines a suitable reagent. You can use lists, smarts, labels to be as specific as needed, but don't try to add too many atoms to your substructure. We have seen that for this example of the amide coupling, that I was just defining a nitrogen, so one single atom in the end. What is also important to know is that R for a side chain is not necessary, as you might be used to in all your 2D drawings. It's not allowed, so CoLibri most likely will give you an error for that. And CoLibri will also complain if the mapping numbers do not match. So they have to match on both sides, on the educt side and on the product side. So no atom lists are allowed on the product side. So you can also, you should use any atoms, so an A instead, if you want to add, or you want to have some kind of atom on the product side. You should also not draw localized bonds when you mean aromaticity on the educt side. So if you would write a new ring closing reaction, it's safer on the product side to draw this alternating of the single and double bonds to ensure that all the atoms are correctly positioned and to do not run into any errors. And the last point is that we see that a lot actually, that you should not draw explicit hydrogens. So you rather define the number of heavy atoms instead than to draw a hydrogen in your reaction definition. Okay, so how to get started in the end. So this is actually always a multidisciplinary project, be it within an academic environment or a commercial environment. First of all, you need to decide what space you would like to have. And if you're doing a proprietary space, you best ask your chemists which reaction can be run with low effort, high yields, and low costs. So this is one of the most important pillars, actually. And then you would go and start writing your first reactions and codings, but you are not alone there, because you should think together with your synthetic chemists which environments are necessary. You have to also be able to, or vice versa, you have to be able to explain to each other what each atom of your reaction should do or should not do, because that is important in the end for these reactions to function virtually. Yes, the next point is also to pre-filter your building block set. So you should not just take your building block set, put it in, and then, yeah, everything will be fine. You can also use pre-filters, things that you don't want to have or will definitely not work. And also there, it's a group project, so you should ask your synthetic chemists which functional groups are tolerated and which ones are not. And task 5, so the last part, which is, I think, a repetitive task, is that you partially enumerate certain reactions within your space and debug your encoding. And also check for unwanted products, and then go into this refinement cycle until you are happy with the products that you get out of your space. Okay, so you made it, and I think I was perfectly in time.